we're just going to start off section 8.3, inverses of matrices, and we'll see what inverses look like. The inverse of a function we know is defined as the function that sort of undoes the other function. If you nest them, if you compose them, take like f of f inverse, they cancel out, and you're left with just the variable, whatever it is. An inverse matrix, similarly, is what undoes the matrix in terms of matrix multiplication. That's the definition of an inverse. If you have matrix A, the inverse is defined by, if you take matrix A, you multiply it by its inverse matrix, you get back the identity matrix. I remember an identity matrix is a square matrix that has ones on the diagonal and zeros everywhere else. So this is the 2 by 2 identity matrix. The 3 by 3 identity matrix looks like this. And you can go on. There's a 4 by 4, a 5 by 5, etc. So if you take the matrix times its inverse, you get the identity matrix of the correct dimensions, correct order. And this is the same thing that you get if you take A inverse times A. So you may recall from just learning about matrix multiplication that matrix multiplication is not commutative. The order does matter in general. If you take matrix A times matrix B, it's not the same as B times A. In fact, sometimes you can take A times B, but you can't take B times A at all. Now, in order for you to take a matrix times another matrix and then flip the order of the multiplication and get the same thing back, something has to be true, and that is that matrix A must be square. You can't find an inverse for a non-square matrix. Okay. Only square matrices have inverses. Only square matrices have inverses. If you just think about it, say, for example, A was 2 by 3. Then in order to get an identity matrix, you'd have to take that times a 3 by 2 matrix, right? And then you could get the 2 by 2 identity matrix in principle, right? But then if you multiplied these in the opposite order, then the result would be a 3 by 3 matrix, and it wouldn't be equal to what you got when you multiply them in this order. Only square matrices have inverses. Not all square matrices do have inverses, though. Sometimes they don't. And there's a term associated with that. If a matrix has no inverse, it is singular. So that's a vocabulary term you need to know. A singular matrix is one that does not have an inverse, and therefore, by contrast, a non-singular matrix has an inverse. If a matrix has an inverse, it is non-singular. Non-singular, not singular, right? So, how do we find this inverse matrix? Well, the definition gives us one way of doing it. If we don't know the inverse, we can say that this matrix times some unknown matrix will get us the identity matrix. So if we take, for example, say we wanted to find the inverse of matrix A, which is 1, 2, negative 3, 4. Say this is our inverse that we want to find, or our matrix that we want to find an inverse of. Well, one way to find that is just by using this definition. We can say, okay, we've got this matrix, 1, 2, negative 3, 4, and multiplying that by some unknown matrix full of variables, whatever. I'll use A, B, C, D, but it doesn't really matter. Gets you the identity matrix of the appropriate order, which in this case is a 2 by 2. Right? And so this is one way we could figure out the inverse. We could say, okay, if I multiply these, I get this. So just using matrix multiplication, row 1, column 1, I can see if I take 1 times A plus 2 times C, then I'm going to get 1. If I take 1 times B plus 2 times D, then I'm going to get row 1, column 2. That's going to be 0. If I take negative 3A plus 4C, then that's going to get me 0. If I take negative 3B plus 4D, it's going to get me 1. And we could go ahead and solve these systems of equations and figure out what A, B, C, and D are. We have 2 pairs of systems that each have 2 equations, 2 variables apiece. We can use those to solve. Now, we're never actually going to write this out because we're going to do something that's a bit of a shortcut. And the reason we do that is because to find the inverse of a 2 by 2 this way, you would need to solve 2 systems of 2 equations each. So that's 4 equations, 4 variables. If you had a 3 by 3 matrix you're finding the inverse of, then you're solving a system that has 3 equations with 3 variables apiece. So it would be you'd have 9 equations, so 3 systems of 3 equations each. For a 4 by 4, you'd have 16 equations to deal with. So you can see that becomes kind of unmanageable. But you might notice something about these systems. You might have noticed already that the coefficients are exactly the same. 1a, 2c, negative 3a, 4c, 1b, 2d, negative 3b, 4d. These 2 systems have identical coefficients, right? If we wanted to write this in matrix notation, the first system would look like this, and that would solve for A and C for us. The second system would look like this, and that would solve for B and D. Like I said, these have the same coefficients, so to solve these, you would do the same row operations. You do the same row operations for this one as you would do for this one. In both cases, you take 3 times row 1, add it to row 2, get something, then you divide to get a 1 here, and then add to eliminate here. And if you're going through Gauss-Jordan elimination, you would do the same exact process for both of these matrices. So instead of writing 2 separate systems, we can write them together. Our coefficients together, and then in this case we want to get 1 for that first equation, in this case we want to get 0. In this case we want to get 0 for that first equation, in this case we want to get 1. So we sort of doubly augment the matrix, and then when we go through our various row operations, we're going to be solving both of these systems simultaneously, and therefore figuring out the whole inverse matrix all at once. Now you notice here, what we wind up getting is our original matrix, colon, identity matrix. So that's how we set up to find inverse. So then we go through Gauss-Jordan elimination. Make a note of that. To find an inverse, you need to go all the way through Gauss-Jordan. No Gaussian. Yeah. So first elimination, take 3 times row 1 plus row 2. Gives me 1, 2. The first row chills out. 0. That's 6 plus 4 is 10. 3 plus 0 and 0 plus 1. Okay. Then I take that second row, divide by 10. Again, row 1 just remains the same. And I get 3 over 10 and 1 over 10. And then finally I can take row 1 minus 2 times row 2. 0. This is still 3 over 10, 1 over 10. And then what do I get here? Let's see, I have 1 minus 2 times 3 over 10. That's 2 times 3 over 10 would be 3 over 5. 1 minus that gets me 2 over 5. And then I have 0 minus 2 over 10. So that's minus 2 over 10, which is minus 1 over 5. And now I've solved my system. Inverse matrix here is 2/5 minus 1/5, 3 over 10, 1 over 10. So we start with A colon inverse matrix. We wind up with inverse matrix colon A inverse. So it happens when we go through this process of Gauss-Jordan elimination. All right. Now notice if we just solve this, we would do the same row operation. When we did this, we would just have this right here. And then we would just have this. And then we would just have this. And so we would have solved for A and C. and gotten those two values. If we were doing this system, we would have had this, 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 and we would have solved for b and d and got negative 1/5, 1/10. So by putting them together in one matrix, we solve for both of them all at once. So instead of doing the same process twice, we just do it all together at once, and then we can solve for our inverse matrix. And we can use that process on 2x2s, 3x3s, 7x7s if we want to. We won't do anything that big, but you can use this process to find the inverse of a matrix, a square matrix of whatever size you want.